Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Abdul Razif bin Abdul Karim. Today I will make a presentation entitled Thermal Management of Solar Photovoltaic System. Firstly, I would like to thank my supervisor, Dr. Roslina Muhammad, for her guidance and support towards my paper. The presentation outline comprises 7 main chapters as shown: introduction, effect of temperature on the performance of solar cell, technologies that address temperature issue and boost the PV efficiency, analysis on the relevant literature, discussion, conclusion, and also Q&A session. First of all, let me derive a bit regarding to this topic: climate change, impact of mining the fossil fuel, depletion of precious resources, and shortage of energy worldwide are among the global environmental concern. Focusing on energy shortage due to it being the most abundant natural resource on earth, easily exploitable, clean, discrete, infinite, long-lasting, and reliable renewable solar energy was selected as the focus point of this research. However, does surface operating temperature and hail impair the conversion efficiency? Furthermore, wind velocity, surrounding temperature, humidity, build-up dust, and also solar radiation are the external environment variable which affect PV module surface temperature. Not all the energy is being transformed into electrical energy. With rises of 1 degree Celsius of the module surface temperature, it resulted in a 0.1 drop in efficiency. The remainder of solar energy is transformed into heat as it complies with the law of energy conversion. The total conversion efficiency is decreased because of this wasted heat. The effect of temperature on the performance of cell. When photon energy E is equal to band gap energy Eg, electron will move from the valence band to the conduction band. When photon energy is larger than band gap energy, surplus energy will be released as heat to the material. When photon energy is less than band gap energy, electron from the valence band will move from the valence band to the conduction bands and back to the valence band. From both of these graphs, the change in open circuit voltage caused by a rise in temperature will always be negative, since Eg over Q is higher than open circuit voltage. The open circuit voltage of the solar cells drops with the rise in its operating temperature. In this paper, there are 8 main technologies that address the temperature issues and boost the PV efficiency: the floating, tracking, concentrating cooling system or FTCC, hybrid solar photovoltaic thermoelectric system cooled by heat sink, hybrid solar photovoltaic thermal cooled by water spraying, PV panel with phase change materials cooling, hybrid solar photovoltaic thermal system cooled by forced water circulation, hybrid solar photovoltaic thermal system cooled by forced air circulation, PV panel with water immersion cooling, and PV panel with transparent coating or photonic crystal cooling. Hereby are the analysis or review done on the related literature which comply the given technologies. They are segregated into technology being used, the selected authors, and its contribution or highlights as shown in the table. Related literature for FTCC and hybrid PVTE with heat sink are as shown. Related literature for hybrid PVT with water spraying and also PV with PCM cooling are as shown. Meanwhile, related literature for hybrid PVT with forced water circulation and hybrid PVT with forced air circulation are as shown. And lastly, the related literature for water immersion cooling and photonic crystal cooling are as shown. Looking into the discussion table, it comprises technology or discussion, disadvantages and also the advantages. For FTCC, the system functions effectively. However, the entire surface is only partly cool when water is sprayed. Among the advantages are high capital cost, evaporation causes water wastage, sprinkler cannot spray the whole surface of the PV module. As for hybrid photovoltaic thermoelectric with heat sink, it has been shown to experimentally lower surface temperature. However, heat sinks become extremely unstable in turbulent airflow. Among the advantages are the turbulent airflow with fin heat sink, heat conduction loss between the hot and cold parts through semiconductor, and the heat is being wasted. Hybrid photovoltaic thermal with water spraying indicates enhanced effectiveness. However, the heat might be utilized to gather additional solar radiation while water is wasted. Photovoltaic with PCM cooling function appropriately. When the PV panel is melting, the mechanism stores the heat. The ability of a substance to absorb, however, deteriorates over time. Plus, more excellent performance in hot weather. Among the advantages are it is less efficient in cold area. Paraffin has low thermal conductivity in its solid state. Segregation reduces the active volume available for heat storage. For hybrid PVT with forced water circulation, it increases electrical efficiency. Due to the continuous flow rate, it cannot attain its ideal state. Hybrid PVT with forced air circulation, the system is quite adequate, although it performs best in cold weather. Additionally, it is less effective than forced water circulation. As for water immersion cooling, the efficiency rose as the temperature dropped. However, during prolonged contact with ionized water, it reduces the electrical efficiency. Photonic crystal cooling eliminates the temperature issue, improve the effectiveness of PV panels. Heat, however, is wasted and may be used for home purposes. As for the conclusion, the following cooling systems are discovered to be promising based on the material used, the capital cost, the performance, as learned through the evaluated studies. Because FTCC sprinkler cannot cover the whole PV module surface area, only a portion is cooled. Evaporation also results in the water loss. A hybrid PV thermoelectric with heat sink can lower the PV module surface temperature. However, the heat sink is extremely unstable due to the presence of turbulent airflow. Additionally, using the lost heat to improve electrical efficiency would be preferable. A hybrid photovoltaic thermal with water spraying showed a realistic efficiency gain discovered through experiment. However, heat might be used to capture additional solar radiation while water is wasted. Using PCM decreased the surface temperature, which significantly improved electrical efficiency. During the melting process, the system preserved the heat from the PV panel, but over time, the material loses some of its capacity to absorb heat. Additionally, this method will not operate equally well in hot and cold climates. A hybrid photovoltaic thermal with forced water circulation effectively increases the efficiency of electricity. Due to the consistent flow rate, it cannot operate efficiently. To ensure maximum efficiency, modifying the flow rate in response to temperature changes is desirable. A hybrid photovoltaic thermal with forced air circulation is practical but more effective in cold than hot weather. Like forced water circulation, forced air circulation is less effective. When the precise submersion depth is used, water emission cooling efficiently decreases PV module temperature and boosts efficiency. Additionally, prolonged contact with ionized water reduces the electrical efficiency. The photonic crystal cooling removes the temperature issue while increasing the PV panel's efficiency. Heat, however, is squandered and may be used for home purposes. That's all is my presentation. We will now proceed to question and answer session. Thank you.